In this lecture, we're going to go over internal energy, enthalpy, and the specific heats and how they apply to ideal gases. For ideal gases, your specific internal energy only depends on temperature. So your specific heats are equal to the derivative of your internal energy with respect to temperature, and this applies for an ideal gas. It's very similar to those of, it's very similar to the equation for incompressible substance. If I were to separate my variables and integrate, I would get that U2 minus U1 is equal to the integral from T1 to T2 of CV of T dt. We can do a similar thing for our specific heat of constant pressure, which is also only a function of temperature. It's now equal to the derivative of enthalpy. Again, if we were to separate and integrate, we would get that H2 minus H1 is equal to the integral from T1 to T2 of Cp of T dt. If we actually differentiate the definition of enthalpy, we get that dH dt is equal to du dt plus R, using the fact that PV is equal to RT. If we plug in our definitions of CV and CP, we get that CP is equal to CV plus R, which is also true on a molar basis. So our two specific heats vary by a constant, and that constant is the gas constant. We also have the specific heat ratio for ideal gases, which is again only a function of temperature. So we have Cp of K is equal to Cp divided by Cv. Since Cp is always greater than Cv, K is always greater than 1. And using our above equations, we're going to come up with another relationship of how Cv and Cp are related to K. So Cp is equal to Cv plus R. So Cp minus Cv is equal to R. So Cp is, if I replace Cv with Cp over K, and I do some algebra, I'm going to get that Cp is equal to K times R over K minus 1. And a similar relationship can be done for Cv. So Cv is equal to R divided by K minus 1. You can get similar expressions on a per mole basis by replacing R with R bar. So your specific heats for selected gases are tabulated in table A20. You can also express your specific heats as a function of temperature, and these coefficients are tabulated in table A21. In addition to that, your internal energy and your enthalpy are tabulated in table A22 and A23. As we're going to look at how to apply the energy balance using the ideal gas tables in our constant specific heats. So we're going to look at a piston cylinder assembly that contains 2 pounds of air at a temperature of 540 degrees Rankine and a pressure of 1 atm. The air is compressed to a state where the temperature is 840 degrees Rankine and the pressure is 6 atm. During the compression, there's a heat transfer from the air to the surroundings equal to 20 BTUs. Using the ideal gas model for air, we want to determine the work during the process. So if I write down my energy balance, I have my change in kinetic energy plus my change in potential energy plus my change in internal energy is equal to heat minus my work. There's no kinetic, there's no potential. So my work is equal to my heat transfer minus my change in internal energy. Q is given. Q is equal to minus 20 BTUs because it is heat out of the system. We need to find our U's. Well, we can look them up in a table. So our T is equal to 540 degrees Rankine. So if I come here to 540, I find that my U is equal to 92.04 BTUs per pound. And at 840 degrees Rankine, I find that my U is equal to 143.98. So my work is equal to minus 20 BTUs minus my 2 pounds times my 143.98 minus 92.04 BTUs per pound. Gives me a total work for the process of minus 123.9 BTUs. So if you are using variable specific heats, you can look up your internal energy as a function of temperature in the tables for ideal gases. We're going to look at another example. In this example, we have air undergoing a polytropic process in a piston cylinder assembly from P1 equals 1 bar and T1 equals 295 Kelvin to P2 equals 7 bar. The air is modeled as an ideal gas and kinetic and potential energy effects are negligible. For a polytropic process, the exponent is N is equal to 1.6. We want to determine the work in the heat transfer using constant specific heats evaluated at 300 Kelvin and assuming variable specific heats. When you assume variable specific heats, you look up your internal energy in tables A22 and A23. So let's start by fixing our state. State 1, P is equal to 1 bar, T is equal to 295 Kelvin. Our specific volume is equal to R T1 over V1 over P1, which is 8.314 divided by 28.97 times 295 divided by 1 bar times 3 over 10 to the 5 to correct my units. V1 is equal to 0.898466 meters cubed per kilogram. And at state 2, we have P2 is equal to 7 bar, N is equal to 1.6. So P1 V1 to the N is equal to P2 V2 to the N. So V2 is equal to V1 times P1 over P2 to the 1 over N, which is 1/7 to the 1 over 1.6 times 0.8466 meters cubed per kilogram. We get that V2 is equal to 0.2509 meters cubed per kilogram. And T2 is equal to P2 V2 over R, which is 7 bar times 0.2509 meters cubed per kilogram divided by 8.314 over 28.97 times 10 to the 5 pascals, 105, 10 to the 5 pascals per bar, and 1 kilojoule is 10 to the 3 joules. we get that T2 is equal to 612 Kelvin. So our work is equal to P2 V2 minus P1 V1 divided by 1 minus N. If we substitute in PV equals RT, we get that our work per unit mass is equal to R T2 minus T1 over 1 minus N, which is 8.314 kilojoules per kilogram Kelvin divided by 28.97. This whole thing is kilojoules per kilogram Kelvin times 612 minus 295 divided by 1 minus 1.6 is minus 151.62 kilojoules per kilogram. So we found our work. Now we need to find our heat transfer. So we're going to do our energy balance. So our heat transfer per unit mass is U2 minus U1 plus our work per unit mass. From table A20, at our given temperature, CV is equal to 0.718 kilojoules per kilogram Kelvin. So our work is equal to CV T2 minus T1. So 0.718 times 612 minus 295 plus or minus 151.62 gives that our heat per unit mass is 75.99 kilojoules per kilogram. If we were to use table A22, our heat transfer per unit mass would be 443.19 minus 210.49 plus minus 151.62, which is 81.08 kilojoules per kilogram. Our original approximation of using constant specific heats could have been improved if we had chosen a value at an average temperature as opposed to room temperature. And again, the problems will state if you should be using specific heats or not. If it does not say assuming constant specific heats, you look up your internal energy base in the table. That's it for this lecture. In our next lecture, we're going to go over polytropic processes for ideal gases.